will stop here and this recording is started. So you can share your screen.
Okay. Screen. Okay. So first, I would like to thank organizers to giving me opportunity to present my research, which will be about non-resonant signals in coherent 2D spectroscopy. And I will start as a motivation with toluene, which is here, which we all know is a transparent solvent, invisible at least. But I experienced when you measure 2D electron spectroscopy in visible regime with a sample dissolved with toluene, you often can see some vibrational coherence that apparently comes from the toluene, which does not absorb invisible, which I was always confused about, and I wondered how it is possible. So the main question today is how can we calculate non-resonant 2D spectra coming from toluene or from other systems or something similar. And it's gonna be only a theoretical talk. I don't have any experimental data, so there will be some equations and simulations. But before thinking about vibrational coherences or stimulated Raman signal, let's start with something simpler. So here is some hypothetical experiment. Here is some cell. You fill it with two-level systems, just two electronic levels, some allow transitions. It absorbs somewhere in UV. Basically closest physical system would be some inert gas like argon or something. So you fill your QL with argon. Then you take visible pulses in red somewhere, pump and probe, and you try to measure a pump probe experiment on a non-absorbing sample. So the question is, or the question would be, what should be the TA signal of a two-level system that does not absorb in the visible? Is it even possible to think about measuring transient absorption of non-absorbing signal? And if so, so what about 2D? So let's start with some theoretical overview, the theoretical background I'm going to use. So the idea is that you have some sample, you shoot several laser pulses into it. So these are their electric field, this E1, E2, and 3, or it can be more. The electric field induces some polarization in the sample, which according to polarization or according to perturbation theory, can be expanded into the terms according to the number of the interactions with the electric fields. For isotropic sample, there are only odd terms. So from the response theory, the first order polarization can be calculated like this. This is here. So this S is the linear response function that comes from the system. It is given by the quantum mechanics of the studied system. This is the electric field. Or third order, which can result in 2D or pump probe, is this relation. So there are three electric fields and third order response of the sample. So once the polarization is calculated, which is the main goal, you can get the electric field that is emitted from the sample, which is just proportional to polarization and shifted by 90 degrees. So the main goal is to calculate polarization, and then you can get the electric field and your signal. So let's start with something very simple because we need to build the theory towards the third order non-resonant signal. So let's start with first order resonant polarization of our simplest system, which is the two-level system here. So this is the polarization we want to calculate. From quantum mechanics, the response function of two-level system is this relation, which is quite simple. It contains some oscillations with the transition energy of the two-level system. It contains the lifetime, basically, of the two-level system and the dipole moment. And we need to model the electric field we use. So we use some very short pulse, which should be this one. So there is the carrier frequency. With the carrier frequency, this is omega, this is the central frequency of the laser pulse. And this is the envelope, which is very, very short. So we assume it's just the delta function. And since we are in resonance, we assume that the laser frequency is almost the same as the frequency, as the transitional frequency of the two-level system. So we can basically plug these two quantities in. We get this relation, which is quite simple, but you see there are exponentials where is the transition frequency of the system minus the laser frequency and plus, the same with plus. And this is almost zero here. So this term is almost one, it's almost constant. On the other hand, this term oscillates a lot. So we take integration over it. It integrates to something very, very small. So we can neglect this term. It's called rotating wave approximation. And finally, we can integrate the thing, and we will get very simple result. Looks like this. So our polarization oscillates with the transition energy of the system. It lives with the lifetime of the system, and the strength is given by the dipole, the transition dipole moment of the system. So here there is a small recapitulation. So we had very short pulse, which was as a cosine wave with the laser central frequency. That was our incoming pulse. The induced polarization lives very, very long and decays with the lifetime of the system and behaves as a sine function with the transition energy or transition frequency of the system. And the emitted wave, there is this phase shift. So it's the same as the polarization, but it's minus cosine. So we see that the emitted field and the incoming are basically both cosine, but there is a minus side, so they can destructively interfere. And if you detect both of them, we basically see the decrease of the electric field behind the sample, which would be the sample absorption. So let's take a look what happens if we go for non-resonant case. So only change in the equation is that we now assume that our laser frequency is much, much smaller than the transition frequency. So in that case, this equation is very, very same, but these two terms both oscillate a lot. So if we would apply a rotating approximation, both would disappear and we would get zero, which is obviously not what we want to go. We want to go deeper deeper into the theory, not to use this level of approximation. So another option would be just not to use a rotating approximation and just to integrate this thing over. Just it's integrable. There is a delta function, so it's fine. And we will get also strange results. Well, it looks basically as the resonant case. There is just one more term, but it's not very so important. It lives with the lifetime of the sample, oscillates with the frequency of the sample. This is also strange, right? The thing is, there is still a logical flaw in this consideration. And the flaw is that if we use delta pulse, it's very, very short in time. It means it's infinitely broad in the frequency domain. So it's resonant with any transitions we want. So this is not the non-resonant case. So we cannot use it like this. So non-resonance interaction cannot be performed with delta pulses. It's inherently effect of finite pulses. So we need to change actually the prescription of the pulse. We would use Gaussian pulse, which is here, and yeah, it appears in the equation here. And now this thing can be integrated as well. It's integrable in terms of complex error function. It's pretty ugly equation, but it can be fit to the computer, fed to the computer, and it can be calculated somehow. But since we are after the third order interaction, we would have to integrate it twice more or something similar to twice more, and that would be mess even for the computer. So we have to make some simpler model or to simplify the relation somehow. So let's do it this way. So this is the same equation as before. Before integration, I just changed the notation a little bit. This is the sum of these two frequencies and difference to make it nicer. And actually, this equation can be reshuffled a little bit. We can take this Gaussian out of the integral to make it here. And now it looks pretty nice because here is just some prefactor. Here is the driving laser pulse. This is the Gaussian pulse we used before. And this is just some complex function, which is defined by this integration, or this, what is less basically in the integration. So this complex function, this is just some complex function. So it changes the amplitude and the frequency of this driving laser pulse. So the only thing that has to be evaluated is a complex amplitude, which actually is fairly easy because if these two numbers are pretty high, if it is higher than 2, it can be approximated by just I over this W, this W. Well, I can show you it's true because if you put some reasonable numbers in, so frequency, the transition frequency 300 nanometers, laser frequency 700 nanometers, 25 femtosecond as the pulse length. These two numbers are high, it's 19 to 124, and it's plotted here. I plot actually IWD, which should be equal to 1 according to this equation. So you see that the for 90 is the blue line, for example. So real part is really 1, and it has some imaginary part which is 0. This is the center of the pulse, And this is basically the, for example, the 2 sigma of the pulse. So we are almost at the pulse, we are in the pulse wing somewhere. So there is some tiny imaginary part, and it goes like this. So in the center of the pulse, it's almost 0. It's almost true. We are neglecting something here. What we neglect actually, it's this imaginary pulse part would actually change the phase of the laser pulse, or on the wings on the wings of the pulse. So basically, we are neglecting some dispersion effects of the sample. And which is the, so I would call actually this approximation instantaneous response approximation, because you see why immediately, because now we can basically plug this approximation in, and we will get very, very simple equation for the polarization, for the non-resonant polarization. You just get the driving laser pulse and some prefactor, which is polarizability. So we now see that the polarization instantly follows the driving laser pulse, the electric field, and which is instantaneous response. And again, summary, so we have like cosine function as a incoming laser pulse, the Gaussian one. Polarization, again, Gaussian. Again, cosine function instantly follows. So the outcoming field should be sine function. As if these two add together, and then basically the electric field propagates through, it gets, due to the sine function, it gets phase shift. And we actually now explain the origin of the order of refraction. And now, okay, let's go for the third order polarization in non-resonant case. And for this, we have to basically do the same thing, but we have just triple integration here. For double level system, the third order response function, this thing is bigger. There are four terms inside, and so on. And yeah, so, and now we need the model for electric field. We don't need just a single pulse. We need actually three pulses. So there are 3 Gaussians delayed by this t and tau, and yeah, by this tau coherent time, the population tau t, and another complex conjugate terms. So this looks like this. And well, we have to calculate this product of three electric fields, which is actually 108 independent terms. It's quite a lot. But luckily enough, we can use, for example, phase matching to get only desired signal. For 2D, it would be this direction. And we are left with 6 independent terms and another 6 complex conjugate. So let's, we have to be a little bit more careful when we have actually finite pulses like this, because it's not so easy. So let's go check, take a look how actually it goes. So these are these 3 pulses. The pulses are these Gaussians. They are delayed. We can control the delay, this coherence time tau, and this t. This is what we can control. And after some time, we observe some signal. But the signal actually happens due to free interaction with the electric field. But the interaction doesn't have to appear during the middle of the pulse. It appears before some, from the signal, before some time t1, and another one is before another time t2, and before another time t3 is actually the first interaction. So it can be somewhere in the Gaussian. And of course, we have to sum or integrate over all possible distributions of them. Luckily, due to phase matching, it's assured that we interact only single time with each pulse. That's nice. But the situation can get a little bit more complicated when the pulses are overlapping. So it's like this. So we cannot assure actually that the first interaction is always with the first pulse. So here on this picture, for example, the first interaction this is still first interaction, but it's with the second pulse. The second interaction is with the third pulse, and actually the third one is with the first pulse. It's just because the finite width of the pulses, and due to in the pulse overlap region. So now we have to care about actually 6 possible ordering of interaction. We have to take care of all of them. Well, actually, in resonant case, it's easy. We usually normally calculate only the normal ordering. The first interaction with the first pulse, second with the second, third with the third. This is the dominant contribution that has that links along, and everything else is kind of weaker, or we can call it artifact. We don't have to care about it. So how is it in non-resonant case? So let's just take just the third time order trend, just the normal ordering, which is just this product of 3 Gaussian. So it's the first interaction with the first pulse, second with second, and so on. We put it here, and we get this formula. Just don't be scared. Only what we can see, want to see is the behavior in the population time. So here, basically this is the rise of the signal is kind of step function, is a little bit washed out due to the finite bit of the pulses. And here, this is the lifetime decay of the thing. So actually, and it's actually strong signal. There is nothing that would make it weak. So it's actually, we would get for non-resonant interaction in the order term from two-level system, you would get something that lives with the lifetime of the sample, which is kind of strange because we all feel that non-resonant interaction should appear only during the overlap region, right? So I was kind of puzzled for some times, but then it turns out actually if you calculate all 6 possible orderings, there's another term that is also very ordered. There's exactly the same one with -1. So it gets cancelled at the end. So if you take actually a look at these 6 possible time ordering, so this is the ordered one, it cancels with another ordering. There is another pair actually that cancels out with each other. And what is left are only these 2 wrong orderings here. So for both of them, that as the last one, you interact with the first pulse, and then there are these both other options. So it actually makes sense because we want to get signal that disappears during the pulse overlap, during the pulse overlap, out of the pulse overlap region. And exactly it's what disappears from in the theoretical point of theoretical side is actually the wrongly ordered terms is what would disappear. So all the signal has to be contained in the wrong time ordered terms. And again, these terms can be integrated with this triple integration, and we would use again the same trick with the instantaneous response approximation 3 times. It's possible to it, and actually it has analytical solution, which is again pretty nice. So we have product of these 3 driving laser pulses. So this is the laser free laser fields, and there is some prefactor, and we have some prefactor, which would be third order hyperpolarizability. So again, the polarization instantly follows not just a single laser field, but this product. And this is actually the polarization of two-level system. And if we have polarization of two-level system, we can make Fourier transform and calculate 2D spectrum. And this is what we have. So this should be 2 levels, the non-resonant 2D spectrum of two-level system, non-resonant approximation. We see that the signal, well, is some imaginary part, some real part. The signal disappears out of the pulse. So in 50 femtosecond, there is nothing. We have 25 femtosecond pulses. And actually, I don't know if this axis, the excitation axis, may have some nice interpretation as it would be in the case in resonant signal. But I can integrate it along this axis, and we can get TA spectrum. So for 0 time, there is no real part. So that would be transient absorption spectrum. So it's kind of naturally what one would naturally expect, that transient absorption change of not absorbed example is 0. But we have something in the imaginary part, which is actually increase of the index of refraction induced by the pump pulse. And this is Kerr effect. And if we let the time fly, so we see that with as the pulses go further apart, the Kerr effects go down. But surprisingly, we see something also, we see something in the transient absorption spectrum, some change of absorption. It looks like change of absorption, but actually it's not. It's a frequency shift of the probe pulse induced by the pump pulse. It's due to the cross-phase modulation between these 2 pulses. So if we have a situation like this, the probe basically overlaps with the trailing edge of the pump, and the pump changes the index of refraction of the sample. And it changes it in a way, so the index of refraction decreases gradually from the beginning of the probe till the later time of the probe. So basically the trailing edge induces some, let's say linear, it's not exactly linear, but linear phase in time for the probe. And if we transform the linear phase induced, we will get the, in the frequency domain, we will get the frequency shift. So this is now here we observe the cross-phase modulation. Okay, so another question is, we have now calculated two-level system. Is it actually a reasonable model for the non-resonant case? Because in the resonant case, it's simple. We can always cover one transition by our laser field. That would be the transition for the two-level system, and we can neglect the rest of the other levels because they are just non-resonant, it will be weak. But in this case, in non-resonant case, actually all levels are non-resonant, equally non-resonant with the sample. So is just two-level system a valid model? And for this, we have to, of course, investigate some multi-level system, what's going to happen. And of course, you know, the theory expands a lot with adding levels. We have to get some nice formalism, and that's formalism of double-sided Feynman diagrams, but we need to adapt it for the non-resonant case. So here is the two-level system, and actually for two-level system, we need 4 diagrams. And then you can see that these two diagrams are actually kind of strange. So for example, here you excite the sample, but the arrow goes out of the diagram. It's the same as here. It's because we cannot use rotating wave approximation, and these basically diagrams would disappear in rotating wave approximation. But now we need them. Also, what we need is that now in resonant case, each diagram would be evaluated as a single term. It can be done pretty straightforwardly. Here it's not possible to do it so, because actually each diagram would evaluate as 6 terms due to different time orderings, as I showed before. So actually we should draw this diagram like this, because the arrowheads doesn't make sense. Also the naming of the k vectors doesn't make sense, because you need to get all 6 permutations here. But it's possible to actually evaluate them. Because each of these 6 different terms, they would look like something like this, because this is a triple integration from the calculation of polarization. This theta would be just these time delays, but you have to, so this is t plus capital T and t plus capital T plus tau. We have to put all possible permutations here. And these W are these frequencies of the individual floor of the diagrams, but not exactly, because I have to add or subtract the laser frequency as well, according to the electric fields. You can do it. I don't go into details. And then you can evaluate it with this instantaneous response approximation, as I showed before. Actually, it can be always done for this first and third argument, because that's condition for the non-resonant response. During the population time, you can have also the optical frequency, the oscillation optical frequency integration or not. So we can evaluate it like this. If you can do all 3 instantaneous approximation, you will get this very easy term, or not. If the W is close to 0, you can get something like this, which is exponential, is complex error function. But now you can do it kind of mechanically. You can feed it to computer, just draw diagrams, and can do anything. For any level structure, you can get a signal. So for example, for 3-level system, with this parallel transition, so you have 2 excited states, both can be accessible from a ground state. You can calculate that if this splitting is large, you get very same result as for 2-level system. Just the prefactor, the signal strength is bigger, because you accumulate more and more terms into the hyperpolarizability. If it is degenerate case, there is 0 splitting, the story is the same. You will get very same picture again. If both dipole moments here are the same, you will get 4 times, not twice, but 4 times the 2-level signal. If the splitting is small, let's say these are vibration levels or 2 closely spaced excited state coherencies, you see something, but I will keep it for later. I don't want to discuss it now. We are not ready for that. Let's go further. You can also imagine another 3-level system. You have 2 consecutive transitions like this. And if you calculate it, you again get just 2-level system, but the amplitude is smaller, because this one acts as an excited state absorption, or analogously to excited state absorption, it just diminishes some signal. And there can be also another interesting situation, is also the 3-level system, but it can happen that your photon energy is non-resonant with any transition, but if you have 2 of them, you exactly hit this second absorbed, second excited state. And in this case, actually, you will get completely different result. And the result is here. You see that in the real part, there is something very, very strong. It's actually 900 times stronger than would be the non-resonant signal of 2-level system. And actually, what we see, it's 2 photon absorption during the pulse overlap region. So you see it disappears during the pulse overlap. So it's very short-living. But the situation is that your pump basically prepares the population at the virtual level, and since the pulses are overlapping, the probe immediately excites it here to the second excited state, and you see then absorption of the probe and the sample induced by the pump. And another option, another system that we can calculate is stimulated Raman scattering. We are basically back to the very beginning when I talked about the toluene, when I talked about some oscillatory signal. So this is the level structure. So there are 2 closely spaced vibration levels. And again, you can calculate it. You can calculate it some short time scale. This is just, again, the region of the pulse overlap. You see there is some strong signal. that disappears mostly during the pulse pulse overlap inside of the pulse overlap region is again the Kerr effect, but it's actually much stronger than, for example, of the two-level system. So this is the Raman-induced Kerr effect, that the Raman scattering can induce increases the Kerr effect of the sample. It's actually used in some experiments as well to measure a Raman spectrum. I found some papers on it. But interestingly, the signal does not completely disappear after the pulses are separated in time. There is something left, and it oscillates with time. It looks like this, and it will actually oscillate as long as is the coherence lifetime between these levels, which can be hundreds of picoseconds in real systems. So it would basically live forever or very, very long. And the structure looks like this. Actually, these are 4 peaks. You can see it in this absolute thing. It's kind of, they are close to each other, so they are actually smeared out, but it would be, in theory, you see, it can be solved analytically as well. So you can really see there are 4 peaks. So this line is the central laser frequency. And these peaks are separated by half of the vibrational quantum along the excitation axis, and they are separated by exactly 1 vibrational quantum along the detection axis. And the signal, of course, the peaks oscillate with the vibrational frequency. Some of them are positive, actually, some negative. It means the imaginary part either follows or precedes the real part. So there are both of them. I don't know now which one is exactly which. And this is the result of the complete the complex interference pattern during this peak. So this is actually how should look like the Raman scattering in 2D. And now let's go for the last result I want to show now is actually the excited state coherence. So what happens now if we have 2 closely spaced levels on the excited state? And I was surprised because the simulation gives me very identical result to the Raman spectrum. It just has opposite signs, so it's multiplied by -1, and it's weaker. It's weak. It's not so as strong as the Raman, but it's 30 times weaker for these parameters I used. So it's not as strong, but it kind of is controversial for me. I still don't understand it because in principle, you don't excite the excited state. You just really excite it's not on the response. You excite some virtual states down here, but the theory, if it is correct, it tells me you should still see weak oscillations coming from the superposition of these 2 states. Yeah, I cannot do much more about it. It can be also theoretical artifact. So the level of approximation is not enough to get perfect 0, or it can be real. I cannot really say. So that's basically all I wanted to show today. So thanks for your attention.
Thank you very much, Jakub. So the floor is open for questions. I see that there's already question. Maybe we can, Daniel Turner has a question. Can we promote him?
Yeah, would it be easy simply to air the question if you...
Well, it's okay. So to read the question. Thank you for the very interesting talk. In the initial analysis, you reduced the 108 terms to only 6 because, as you stated, the phase matching condition. What phase matching condition did you take? If the box geometry, how does that work for phasing of 2D spectra to the TA, which of course is not conducted in a box geometry, but rather the pump probe geometry? I worry the projection slice theorem may not apply directly if you need more terms in the pump probe geometry rather than the box geometry. The other difference is that in a TA case, there's only 1 pump pulse, and therefore the contributions from misordered terms may be distinct from a case where the 2 pulses have some overlap, but not perfect overlap. Thank you for contributing.
Okay, well, that's an interesting question and a very complex one. Actually, I don't know. Actually, I did not check if the projection slice theorem works. I would assume so, but that doesn't have to be the case. So in case, if it does not work, the phasing for the signal measure in boxcar would be difficult. And I don't know how to deal with it. I don't have I don't have any smart answer right now. That's it, yeah. If you measure it with shaper, it should be phased and it should be easy. And otherwise, I don't know. one should verify if the projection slice theorem works and try to phase it to PAM-Pro. That's my answer, basically.
Can I comment on that, Thomas?
Sure. Sure.
Oh, thank you very much. In my view, at least, well, from what I seem to remember experimentally, okay, it works because, well, we used quite often those signals from the solvent, okay, for calibrating the zero delay, which is very, very convenient, right? Because it gives you very nice dependence on their, well, pump probe, let me put it this way, okay, overlap, and especially when you have to deal with the white light continuum, right, which is stretched in time, okay, so you would like to understand where each color arrives, okay, so to me, this result is not surprising, but I might be missing something here.
Okay. So I see that I might have a bit of a problem. I'm probably not co-host, so I cannot promote people to the panel. So John Wright has a question, but maybe we can ask, or Pavel Mali can ask his question first.
Okay, hi Jakub. I have a first comment to this same direction as Maxim. So actually, we tried this. I was also interested. So we measured. I measured 2D and pump probe just on a BBO, on the crystal of BBO. So completely off resonant, you know, to see if you can see the same time the second harmonic and the signals and so on. And the projection slice theorem seems to work very well. So so it seems that you really see the traces, and I was also very happy to see your wiggles, you know, like in the spectrum, because we also see them. So we measured in the pump probe geometry, and then we have very nice horizontal wiggles in the spectrum. So I do think it works, and I do think that the projection slice theorem works, at least from experimental point of view. It's interesting talk, yeah.
And I would like, maybe now I would like to comment on Pavel's comments on my comment that I was also quite happy to see that, because I guess you are about to publish these results, right?
Yeah, it's under review now, yes.
Okay, good. Because quite often we are asked for, well, I'm taking, well, many things for granted, right? But sometimes the reviewers would like to know, we are at what, let's say, theory we are basing our approximation measurements, right? So that would be very nice to have your paper as a reference.
Mm-hmm. Okay, good.
So that's practical question. Okay, John, I think I promoted you to the panelist. Okay, so please go ahead.
Yeah, okay, I think you can hear me. So I just wanted to comment that Bloomberg did the same kinds of things in the frequency domain, where it's much easier to get something like a non-resonant background. It's basically, you know, the transition moment for electronic transitions times the density matrix for whatever you've got, you know. So it's the same approach basically as getting the index of refraction. But I also wanted to point out that that last example that you gave, where you had a coherence, a zero quantum coherence between the two upper electronic states, that was also something that Bloomberg treated. He called it Pier 4, P-I-E-R 4. And it was basically a resonance that you see even, you know, between the two lasers that you've got driving this coherence, but they're not resonant themselves. And so it was, but he also showed that you had to have dephasing occurring in order to get those kinds of resonances. And then Robin Hochstrasser followed that up with another experiment where he showed the same kinds of things in molecular samples.
Okay, I can check it out and cite it then. Okay.
Yeah. So just for your information.
Okay, thanks a lot.
Okay, any other questions? So maybe I can ask a question here. So this is, well, from at least from some perspective, it's like signals that you might not really actually want to see. Normally we like to see the resonant kind of signals, but could you imagine something where this is actually useful, except for, of course, it's useful to understand what kind of contaminating signals you might have, but can you actually learn something from some of these experiments?
Yeah, that's a good question, of course. I think it would be actually difficult. Well, you can, of course, use it as to subtract the artifact or something. But, well, the signal is mostly reflects your laser pulses more than your sample. You know, the position in the spectrum is given by your laser frequency. The shape is also given basically more by your laser than the sample. Most of the sample information is actually hidden in the intensity of the signal than in the shape. So I would say it would be difficult, but there might be something. Somebody smart can find out something. Maybe for the two photo absorption might be different a little bit. I don't know. Actually, myself, I didn't find anything immediate how to apply it. Yeah.
Let me add on to that. There is actually a very useful way to use non-resonant background if you have a resonant signal as well. So in the experiments where you have, toluene, you'll have both a non-resonant background and you'll have vibrational modes. And those two will interfere with each other and change the line shape. And by fitting the line shape, you can find the ratio of the resonant to the non-resonant third order susceptibilities. And if you know one of them, then you can get the other one. So this is a great way to get absolute values for your third order susceptibility.
Okay. Any other questions? If not, then let's thank Jakub again. And